Welcome to Advanced Calculus 1. Today we begin Lesson 1, Completeness and Suprema. Today we will follow this roadmap. First, we discuss why an order field is not enough. Second, we will introduce the Completeness Axiom and the concept of Supremum. Third, we study the approximation property. Fourth, we prove the Archimedean Principle. Fifth, we prove the density of rational numbers. Finally, we discuss infimum, reflection, and monotonicity. Now let us begin with the main problem. An order field structure is not enough. Inside an order field, we can add, multiply, and compare numbers. However, this still does not guarantee that every limiting process stays inside the field. This is the central issue. Now consider the rational numbers. We denote them by Q. Define the set S as follows. S consists of all rational numbers x such that x squared is less than 2. This set bounded above in Q. However, it does not have a least upper bound in Q. Generally, the boundary should be the square root of 2, but the square root of 2 is not rational, so Q contains a gap. This is why completeness matters. Now we introduce one of most important actions in real analysis, the completeness axiom. The axiom says the following: if E is a non-empty subset of R and E is bounded above, then E has finite supremum in R. Now, why do we need this axiom? The key idea is that R has no missing least upper bounds. In other words, if a set has an upper bound, then there exists a smallest possible upper bound. And importantly, that Suprema exists inside R. This axiom becomes the foundation for many later results in analysis. For example, limits, continuity, compactness, and integration. Now we define upper bound and supremum. A set E is bounded above if there exists a real numbers m such that A is less than or equal to m for every A in E. The suprema of E is the smallest possible upper bound. Now let us look at a simple example. Suppose E equals the closed interval from 0 to 1. We claim that the suprema of E equals 1. Why? Because every E has less than or equal to 1. So 1 is an upper bound. Also, 1 itself belongs to E. Therefore, no smaller numbers can be an upper bound. Hence, sup E equals 1. We now make two basic remarks. First, if a set has one upper bound, then it has infinitely many upper bounds. Because if m is an upper bound, then m plus c is also an upper bound whenever c is positive. Second, if a suprema exists, then it is unique. Now consider the following question. Suppose E is a subset of Z. If subset exists, must sub E belong to E? To answer this, we need to understand how close element of E can get to the supremum. This motivates our next theorem. Now we arrive at one of the key properties of the supremum. Suppose E has a finite supremum, then for every epsilon greater than 0, there exists an element A in E such that sub E minus epsilon is less than A, and A is less than or equal to sub E. The iteration is extremely important. If S is truly the smallest upper bound, then elements of E must get arbitrarily close to S from below. Otherwise, we could lower the upper bound. Now, let us prove the theorem. Let S equal sub E, and let epsilon be greater than 0. Since S is the least upper bound, any number strictly smaller than S cannot be an upper bound. In particular, S minus epsilon cannot be an upper bound of E. Therefore, there exists an element A in E such that A is greater than S minus epsilon. Also, epsilon is an upper bound of E. We have A is less than or equal to S. Combining the two inequalities, we obtain S minus epsilon is less than A and A is less than or equal to S. This slide contains an important correction. The proof should contain actually A is less than or equal to S. There should not be any typo of actual text. So, the final conclusion becomes sub E minus epsilon is less than A, and A is less than or equal to sub E. Now, we return to our earlier question about integer sets. The theorem says if E is a non-empty subset of Z, and E has a finite supremum, then sub E belongs to E. Why does this happen? Because integers are discrete, then they have gaps of size 1. So if an element gets within distance 1 of the supremum, it must actually reach the supremum. Now, let us begin the proof. Let S equals sub E by the approximation property. Using epsilon equals 1, there exists an element A in E such that S minus 1 is less than A, and A is less than or equal to S. We now claim that A is an upper bound of E. Take any element X in E. Since S equals sub E, we know that X is less than or equal to S. Also, from S minus 1 is less than A, we obtain S is less than A plus 1. Therefore, X is less than A plus 1. Now, remember that X and A are integers. Since X is less than A plus 1, and both numbers are integers, this implies that X is less than or equal to A. Therefore, for every X in E, X is less than or equal to A. So A is an upper bound of E, but A also belongs to E. Therefore, A is maximum element of E. Hence, sub E equals A, and A belongs to E. Now, we discuss an important transition in analyze. The approximation property says the following. For every epsilon greater than 0, there exists an element A in E such that sub E minus epsilon is less than A, and A is less than or equal to sub E. In analyze, we often do not want to use an arbitrary epsilon. Instead, we prefer a more concrete quantity. For example, 1 over n. So, conceptually, we replace epsilon with 1 over n. But to do this rigorously, we need the following fact. for every epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon. And this leads directly to the Archimedean Principle. Now we introduce the Archimedean Principle. This theorem connects real numbers with natural numbers. Formally, it says let a and b be real numbers with a greater than 0. Then there exists a natural number n such that b is less than a times a. Intuitively, if we keep adding enough times, we will eventually exceed any number b. Now let us prove the theorem by contradiction. Assume for contradiction that n times a is less than or equal to b for every natural numbers n. We then define the set. E equals the set of all NA where n belongs to n. This set is non-empty, and by assumption, it is bounded above by b. Therefore, by completeness, E has a supremum. Let S be equal sup E. Since A is positive, S minus A cannot be upper bound of E. Therefore, there exists a natural number n such that S minus is less than NA. Now, add A to both sides. Then we obtain S is less than n plus 1 times A. But n plus 1 is also a natural number. So, n plus 1 times A is an element of E. This contradicts the fact that S is an upper bound of E. Therefore, our assumption was false. Hence, there exists a natural number n such that B is less than NA. Now, we obtain an important corollary from the Archimedean Principle. The corollary says, for every epsilon greater than 0, there exists a natural number n such that 1 over n is less than epsilon. This result is extremely important in analysis because it tells us that 1 over n can become arbitrarily small. And this is actually why we often replace epsilon with 1 over n in proof and constructions. Now, let us prove the corollary. We apply the Archimedean principle with A equals epsilon and B equals 1. Then, there exists a natural number n such that 1 is less than n epsilon. Since n is positive, we may divide both sides by n. Therefore, 1 over n is less than epsilon, and this completes the proof. Now, let us apply our new tools to an actual example. We define two sets. The first set A is 1, 1/2, 1/4, and so on. The second B is 1/2, 2/3, 3/4, and so on. We will prove that the Suprema of A equals 1 and the Suprema of B also equals 1. First, we prove that sup A equals 1. Notice that 1 itself belongs to A, and every element of A is less than or equals to 1. Therefore, 1 is an upper bound of A. But since 1 belongs to A, any upper bound of A must be at least 1. Therefore, 1 is the smallest upper bound. Hence, sup A equals 1. Now, we prove that sup B equals 1. Every element of B has a form n over n plus 1, and this quantity is always strictly less than 1. Therefore, 1 is an upper bound of B. Now, let m be a number strictly less than 1. then 1 minus m is positive. By the Archimedean principle, we can choose a natural number n such that 1 over n plus 1 is less than 1 minus m. But observe that n over n plus 1 can be rewritten as 1 minus 1 over n plus 1. Therefore, n over n plus 1 is greater than m. So, numbers smaller than 1 can be an upper bound of b. Hence, sub b equals 1. Now we move toward another important theorem. The Archimedean principle allows us to control small quantities. For example, we can guarantee that 1 over n is less b minus a. But in analyze, we often need something more concrete. Give two real numbers with a less than b. We want to find an actual rational number q such that a is less than q and q is less than b. This leads directly to the density of rational numbers. Now we introduce one of the most fundamental properties of the rational numbers. The theorem says if a and b are real numbers and a is less than b, then there exists a rational number q such that q is less than q and q is less than b. The key idea is simple. No matter how small an interval becomes, there is always a rational number inside it. Now let us prove the theorem. Let a and b be real numbers with a less than b, then b minus a is positive. By the corollary, we may choose a natural number n such that 1 over n is less than b minus a. Multiplying by n, we obtain nb minus na is greater than 1. This means that the interval from na to nb has length greater than 1. Therefore, it must contain an integer m such that na is less than m and m is less than nb. Now define a equal m over n. Since m is an integer and n is a natural number, q is rational. Now divide the inequalities n a less than m less than nb by n. Since n is positive, the inequalities keeps the same direction. Therefore, a is less than q and q is less than b. Thus, we have found a rational numbers between a and b. So far, we have focused on upper bound and supremum. Now we study the lower side. A set E is bounded below if there is a real numbers m such that m is less than or equal to a for every a in E. The infimum of E is the greatest lower bound. In other words, it is the highest possible floor. Finally, a set is called bounded if it is both bounded below or bounded below. Now we introduce another important symmetry in analyze, the reflection principle. Suppose E is a subset of R. We define negative E as a set obtained the reflecting every element across 0. The theorem says E has a suprema if only if negative E has an infimum, and moreover, the infimum of negative E equals negative sub E. Similarly, infimum result can also be translated into suprema result. This theorem tells us that suprema and infima are mirror images of each other. Now let us prove the first part of the theorem. Assume that S equals at sub E. We will prove that negative S equals infimum of negative E. Take any element y in a negative E. Then by definition, y equals negative x for some x in E. Since S is the suprema of E, we know that x is less than or equal to S. Multiplying by negative 1, we obtain y is greater than or equal to negative S. Therefore, negative s is a lower bound of negative e. Now we continue the proof. Let t be any lower bound of negative e. Then for every x in e, we have t is less than or equal to negative x. Multiplying by negative 1 reverse inequality. So we obtain x is less than or equal to negative t. This means that negative t is an upper bound of e. Since s is the least upper bound, we have s is less than or equal to negative t. Multiplying by negative 1 again, we obtain t is less than or equal to negative s. Therefore, negative s is the greatest lower bound of negative e. Now we introduce our final major theorem, the monotone property. Suppose A is a subset of B and both sets are non-empty. Then, if B has a supremum, we have sup A is less than or equal to sup B. Similarly, if B has an infimum, then infimum of A is greater than or equal to infimum of B. Initially, if we enlarge a set, its ceiling can only move upward, and its floor can only move downward. Now let us prove that theorem. Let S equal sup B. Since A is contained in B, every element of A is also an element of B. Because S is an upper bound of B, we know that x is less than or equal to s for every x in A. Therefore, s is also an upper bound of A. But sup A is the least upper bound of A. So, sup A is less than or equal to s. That is, sup A is less than or equal to sup B. For the infimum statement, we apply the previous result to negative A and negative B, and then use the refraction principle. Let us briefly summarize what we learned today. First, Q is an ordered field, but it is not complete. Second, the completeness axiom guarantees the existence of least upper bound in R. Third, Suprema can be approximated from below. That is, sup E minus epsilon is less than A, and A is less than or equal to sup E. Fourth, the Archimedean Principle allows us to control arbitrarily small quantities using 1 over n. Fifth, every open interval contains a rational number. This is the density of rational numbers. Finally, infimum result can be obtained from supremum result through refraction. And this completes lesson 1. Thank you very much.